Hello and welcome back to Calculus 3. So today we are talking about directional derivatives. We are supposed to see now how to take derivative in any direction. Remember that derivatives measure change. The easiest way to picture that is, as I said, on some kind of a terrain where partial derivatives correspond to the change in elevation, so measure the change in elevation, but only in direction of x-axis for partial derivative with respect to x, and direction of y-axis for partial derivative with respect to y. The goal of this lecture, 12.6, is to introduce directional derivatives, which is directional derivative. It will be a derivative in any direction you want. So now let's see how we're going to do it. So we have some kind of a terrain with x-axis and y-axis underneath, with this z-axis going that way. So now I am going to have my red path on top of this hill going that way. The blue path has to be, let's say, going this way. So these are the two paths that are on the top of the, let's say, top of the hill, right on the surface of the hill. And what I did, as I said, that the blue path is above the y-axis, and then you have the derivative, like measure. So there will be this tangent line here, at the point, and now that point is on the y-axis, above y-axis, and then we can have a point on the red one, which is going to be the point on x-axis. And you can find the two tangent lines. As you can see, as long as you are working on, so this would be fx, and the blue one would be fy, partial derivatives, the slopes. I mean, that's m equals, right? So what happens is the partial derivatives will take that into account. Now, you can say that x-axis is, let's say, east-west. So, sorry, west over here and east over there, so east-west. And then have the other one to be north and south. What happens if someone wants to go southeast or at any angle in any other direction? How do we find that derivative? Because, yes, this line is, the blue line is wavy, because it sits on the top of the hill and measures the change in elevation, right, the change in height at every point using the slope. And then the same thing happens with the other one. Now, what happens, because we know that in any other direction, you pick any other point, so let's pick this point here, there will also be a derivative going down the hill, or derivative going up the hill this way. So we can go in any direction, put any point anywhere, and you can go in any direction 360 degrees around you. Can we find the change in any direction? And that's what the directional derivative is for. So directional derivative is going to take in consideration two elevations that we have, which is the x direction and the y direction, and it's going to change both directions. So now I'm going to have, again, definition part, and then I'm going to have the computation part. So directional derivative would be, let f of xy be differentiable at point A, B. So this is any point that it's not on axis. It could be, but why would you? And let U be the unit vector. So I hope you see that we are getting the magnitude from F and the direction from U. So let U be unit vector in xy plane. The directional derivative, so directional derivative in direction of U of F at AB is given by good old limit h goes to 0. We know what the definition for the derivative is. We have f of a plus ag1 comma b plus hu2 minus f of ab divided by h. So standard definition for the derivative, except as you can see now we are adding plus h part to both of the components, not just one at a time. So when we did plus h to one at a time, that was those were the partial derivatives, x and partial derivative of y. We did that yesterday. Those definitions were here, right? So you see x plus h comma y and x comma y plus h. So those were partial derivatives. Today, both of them are varied at the same time, and each h is actually multiplied by components of u because it's supposed to take on that direction. All right, good. That was interesting. It sounded like a seal died or something, but all right. So now we're going to find. Now we're going to use a theorem. We're going to write down the theorem, and this theorem is actually the way we compute directional derivative. So the premises are the same. You have to have differentiable function, and you have to have a unit vector. So let f of xy be differentiable at AB, and let u, and you see me put the hat, so you know it's a unit vector. Good effort. Then here is the way to calculate. So this is the formula we will be using. Directional derivative of function f computed at AB in the direction of vector u. It's a lot of information in one piece, right? That would be the dot product between the vector of partial derivatives computed at AB dotted with vector u. So remember that the partial derivatives, they're giving you magnitude, and the vector u gives the direction, and this is why this is directional derivative. You can find the derivative, you can find the change in any direction. Vector u will provide the direction. It has magnitude 1, so it will not be changing the slope of the line that goes in that particular direction. So there you go. This is the formula that we will be using to find the derivative in any direction. Actually, it's, wait, I'll put on a cloud. There we go. Okay. So find the directional derivative at 3, 1 for f of x, y given as x squared y minus 3y, whatever, in the direction of vector u equals 3, 5, not 3, 4. Let's see what you get. What happened?
Why did I before we do?
No, it's 3, 4. Okay, let's take a look. So the first thing is the unit vector. Vector that is given there is not a unit vector. You can't use it in this calculation. You have to find the unit vector first. Do that in blood over here now, because that kills the grade every time. So, oh, I see a lot of erasing going on. Vector u is equal to vector u divided by its magnitude. This is your first order of business. Pretty much all of the time you're going to have a non-unit vector there. The magnitude of 3, 4 is 5, therefore it's not a unit vector, right? So we divide our vector 3, 4 with magnitude 5, and the unit vector we need is 3/5 and 4/5. The rest is just, plug stuff in. So I'm going to find this vector of partial derivatives first, and then I'm going, so to find fx is simply 2xy, and then fy is x squared minus 3. So now fx computed at AB, which is 3, 1, is 2 times 3 times 1, which is 6. And fy computed at 3, 1, that's the point that we want, is going to be 9 minus 3, which is 6 again, whatever. So now the directional derivative in direction of unit vector u of function at 3, 1, it's a lot of information in one little notation over there, is the dot product between 6, 6 and 3/5 and 4/5. So that's going to be 18/5 plus 24/5 for the total of 42/5. So 8.4. It's the dot product, so obviously the answer to this is going to be scalar. Good. Now that would be the slope of the tangent line that you can find in the 2D realm, right? For y equal mx plus b, except now you don't have y equal mx plus b because it's not in the direction of x-axis to have mx. But that's how much the value changes at that point. So that, because derivative measures the change. So now that we have the way to compute these directional derivatives, we are going to take this very important part of the vector, this one over here, and we are going to give that one a name. It's going to be called the gradient. Gradient is going to be a vector, a collection of partial derivatives. So gradient, we are going to have the notation for the gradient, which is going to be del f, like this. So gradient del f of xy is simply a collection of first partial derivatives. So we're just giving it a name, guys. That's all. We have one for 3D as well. So if you have x, y, z, you can put it. We can redefine our derivative in direction of u as gradient of the function computed at AB dotted with the u hat. So it's now it compresses the definition. Once we don't have to write out the vector, we can just now compress it into the gradient. So now we can do this as a vector form. This upside down triangle is read as del. So if you have this, you will read that as del f. That's the way you pronounce. And we have the vector above it because it's a vector. It's a collection of partial derivatives. So that's the notation. All right. Now, for all of you, this is so simple, right? You know how to find first partial derivatives, and you know the concept of a vector, which is just stuff everything in a vector. Next time you're out, write this casually on a napkin and just leave it around, see what happens, right? For you, this is zero effort, right? You go to the restaurant, you just have a bar napkin or something, and you just write the definition, just leave it there. Oh. I do that. If I go on a vacation or a restaurant or something, I just write something on a paper and just leave it there and walk away. Let them wonder what happened. Like, why? Can you leave it for like 5 seconds? You went out to dinner? No. It's the only 2 times I do math, right? When I'm in class and when I'm in a restaurant, that's it. You have to have fun with this. People around me learn never to say, what do you know? You know, the figure of speech. Because I immediately pull up some kind of theorems. Like, I know this one. You know this one? Like, can you even spell it? All right. So, we have partial derivatives with respect to x and y, which measure the change only in the direction of x-axis and the direction of y-axis. Then we combine the motions and multiply by direction the unit vector u, and we come up with a directional derivative which measures the change in any direction. And then we take this one part of that formula and we give it a new name. We define that as the gradient of the function. And we put the notation on it, del f. And that's it. So now we want to study directions of change. So the theorem, again. And this is now important stuff for application. So everything up to this was mathematical gymnastics, right? You just define terms and you can do meaningless problems with x and a y, no one cares. Now you come up with a theorem, which is what physicists use to connect it to the real situation, and then engineers use that to create stuff and understand stuff. So it's maximum rate of increase at AB in the direction of del f AB. The rate of change is del f AB. So function has its maximum rate of increase. So rock climbing, and then hiking up the steep hill and the mountain, and then casual walking, and then you walking on this flat surface over here, right? So think about those. So for most of us, right, the response is, what is the least demanding terrain to walk on to get from point A to point B, right? Can we avoid the stairs? Can we avoid any kind of steep hill, right? Is there an easier kind of way to get from point A to point B. For those that like rock climbing and hiking up the steep slopes, they actually say, what is the worst possible right slope that I can find? So the function has its maximum rate of increase in a direction of the gradient FAB. So at every point, right, you can, once you calculate the gradient, there will be a derivative there that will point in the direction of the steepest. So think about being at the edge, right? And at this point, you have infinitely many different ways to go. You can go up, you can go down, but you can go in any other direction. And all of these directions, there are infinitely many because the vector pinned at that point can point in any of the 360 degrees, right, around directions, and in between, obviously, so infinitely many. Only one of those directions will be the steepest way up, right? The hardest way to climb. And now we have the next one is the maximum rate of decrease. So it would be the easiest way down, the steepest way down. And that will be the negative gradient. So f has its max rate of decrease at AB in the direction of negative gradient f AB. The rate of change at the direction is negative gradient. The magnitude, I mean. The rate of change is negative del FAB in absolute values for the magnitude. So this is the same thing, except now you're going down the fastest. So the first one tells us the fastest way up, which is the steepest way up. If you are looking to change your height fast as possible, you are looking for the fastest way up, and the fastest way up will always be in the direction of the gradient. Now, the negative gradient will give you the fastest way down. And then the directional derivative is 0 in any direction orthogonal to the gradient. Yes?
So for number 2, you just multiply by -1?
Yes. Mm-hmm.
Oh, that's it?
That's it. It's Calc 3, of course that's it. Yesterday in Calc 2, I did trigonometric substitution and partial fraction decomposition in 3 hours, and we had casualties. When you take Calc 2 in a regular semester, you know, that happens over a course of a week and a half. Well, it happened yesterday in 3 hours, and some students were so pale by the end of that lecture that the others, one had the carpal tunnel, you know, one broke the arm trying to write the stuff down. It was, yeah. Over here, you just multiply by -1 between number 1 and number 2, and that's that. So, yeah. Yesterday's lecture was actually, you know, following the previous from Monday, and that was integration by parts and trigonometric integrals. So there you go. Right. So you have those 4 heavy hitters in 6 hours in 2 days. Anyway. So now directional derivative. Is 0 in any direction orthogonal to the gradient. and the problems that you are dealing with are steepest ascent and steepest descent, right? So let's find the problem in the here. Let's find something interesting. Oh, this is bad enough. All right, so problem 32. We have the surface fxy is equal to 2 sine of 2x minus 3y. At the point P that is given as 0 pi, and find this let's find the vectors that give the directional steepest ascent, steepest ascent and descent, and then calculate the magnitudes, right, to tell you the rate of the direction. So let's see what you guys come up with. right? It's a wave, and at one point, clearly, you are going to have the fastest way up, the fastest way down. If you are at the top of the wave over here, going left, right like this, you are not changing the height, altitude at all, right? Going down the wave, right, would be the fastest way down. If you are here, going straight up is the fastest way up. But you can also go on a side, which is not detected by this. so that's what this is, and clearly, if you are steering a ship, you gotta know that stuff, right? Otherwise, you are going to ruin your and everyone else's lives very quickly if you are steering in a wrong direction. Software is piloting only when it's, you know, calm and nice and dandy. In any case of emergency and seas getting rough, which is technically what we have as a function right here, you better know these kind of things to be able to work your way through it. So now we are going to compute this. We find our partial derivatives. So fx is going to be 2 cosine of 2x minus 3y times 2 for the total of 4 cosine 2x minus 3y. And then fy is going to be 2 cosine 2x minus 3y times negative 3 for a total of negative 6 cosine of 2x minus 3y. So now del f computed at 0 pi is going to be 4 cosine of x is 0, so that dies, of negative 3 pi, and then negative 6 cosine of negative 3 pi. And we actually compute this because it gives us the vector, which is the direction in which the change is maximum, going up, right? So that's going to be cosine at negative 3 pi. So cosine of negative 3 pi, you draw the cosine function, and this one over here is positive pi. So then the next dip like that is positive 3 pi. That's the 2 pi right there. Since cosine is symmetric, it's going to be negative 1. So we have negative 4, 6. Bueno? You can draw this way as well. This is your negative pi, and this is what we are looking for, negative 3 pi. Right there, negative 3 pi. So negative 3 pi. But since cosine is symmetric, you can just do the positive side and then take the same value. So that's a negative 1. The answer is negative 1 for cosine of negative 3 pi. Also, you can say cosine is even function. So for cosine, cosine of x is the same as cosine of negative x, which is another reason why I did this, right? It's even function, symmetric on the y-axis. I don't care which way you compute this. The importance is that the max rate of increase is in the direction of 4. So max, well, steepest ascent, right? That's the wording they are looking for. Let me see. Yep, steepest ascent. Would be the vector negative 4, 6, and then the rate for it will be square root of 16 plus 36 equals to square root of 52. And then steepest descent would be for negative 6. So just multiply by negative 1. and the rate for that one is negative square root of 52. So the fastest way up, the fastest way down. Nice. Okay. That's that. Now you can use this to figure out the maximum rate of increase of the temperature within the 3D object, the change of its density. There are a lot of things that you can do. If you need to measure the change, derivative does it. Now, if you are measuring the two-dimensional change, that's calculus 1 derivative. But if you have 3 or more variables, it's going to be the directional derivative, because generally you don't deal with the what's fx, right? If you are using directional derivative and you're just looking for fx, you just do calc 1, because fx is just the y direction. I'm sorry, the x-axis with the z-axis. That's technically calculus 1. So there is no need for just working out with the fx, the partial derivative with respect to x. Just calc 1 problem. Most of the time you will be dealing or trying to figure out which way the temperature spreads the fastest. I mean, you are mechanical engineers, right? And these kind of things. So you are in chemical engineering, material engineering, structural engineering, civil engineering. These are the things that you worry, right? The materials and how they behave and the densities and so on. So you have to find the fastest change up and the fastest change down, whether it's temperature or height or density or whatever concept you're dealing with. So that's that. Just say bye and see if this